Good morning, students. So today I am going to discuss the first chapter, relations and functions. In this chapter, the relations and about functions that are all discussed in the regular classes. So relation and the types of relations, functions and the types of functions. Here in this chapter, remaining concepts are it is the invertible functions. Invertible functions is one concept. It is remaining in this section. So second one is bijective function. Now it is binary operations. Binary operations is the second session in this chapter. Before we are going to discuss this invertible functions. So we are going to know some basic concepts that are required to define this invertible functions. Basic concept means the types of functions. So usually in our regular class we know that there are 5 types of functions. So the first one is that it is one function. Second one is that it is many one function. Third one is that onto function. Fourth one is that into function. So fifth one is that it is the one and onto function. And onto function. The first function, it is one function, can also be called as it is injective function. The third function, onto function, is also called as the surjective function. So the fifth function, one and onto function, can also be called as the bijective function. Bijective function. Say one function means if you consider f, it is any function from the non-integer capital A to the non-integer capital B. This function from A to B is said to be 1. The condition is that the different elements in the domain have the different images in the codomain. Means if you consider here in the domain x1 and x2 are the 2 different elements in the domain, if you consider, for which here the corresponding images under this function in the codomain are f of x1 and f of x2. These are also different. Means that the different elements in the domain have the different images. Then we say that this function is one function or injective function. Similarly, so many one function means the 2 different elements in the domain have the same image for the many one function. So for the onto function means here each element, that is y in the codomain, is the image of some element x in the domain. It means that for each, so y belongs to capital B, there exists some element x belongs to A, such that it is f of x is equal to y. This means that the given function is onto function. Here onto means each element of the codomain is the image of at least one element of the domain. It means that each element of the codomain is the image. Each element of the codomain is image means the set of all image elements are called as range set. So the onto function can also be defined as Any function from this set A to B is said to be onto. Here the range of this set f must be is equal to codomain, because here the function is said to be onto. The condition is that each element of the codomain is the image of at least one element of the domain. Means here the elements present in the codomain are the set of all image elements. The set of all image elements is nothing but range set. If the range set is equal to codomain, then that function is always called as onto function. So here lastly it is one and onto function, or it is bisective function. Means any function it is satisfied both one and onto condition, that is called as it is bisective or one and onto function. So that all discussed in the regular class. So here examples also completed on this section. So now here the invertible concept I am going to deal here. Invertible function. Invertible function means if you consider any arbitrary function f from the arbitrary set capital A to the arbitrary set capital B. So here this function from the set A to B is said to be invertible. Here is said to be invertible. Here there exists another function, you call that as g, right? There exists another function, you call that as g, from the set B to A, that is from B to A, such that their composition from F to G, it means that GOF must be is equal to the identity function in the domain of F. The identity function in the domain of F, it is usually denoted by I. A means the identity function in the domain of F, and the composition from G to, that is G to F, it is as FOG must be is equal to the identity element in the domain of G, that as identity function or identity element in the domain of G means it is as ID. Here this function is and this function, if both the functions are satisfied these two conditions, then this function G from this set B to A is called as the inverse of the function F. That is usually denoted by G is equal to F inverse. This is the notation. So here you may also take this G as F inverse or the inverse of the given function G, when if F and G are satisfied both these two conditions. See, from this it is also clear that if these two functions these two functions are satisfied these two conditions, it means that the identity function in the domain of A, the identity function in the domain of G, if these two functions are satisfied, then the given arbitrary function f from A to B, it is always a 1 and onto function, right? So conversely, if f is a function from A to B is both 1 and onto, then there always exists another function, you call that as G from B to A, such that their composition GOF is equal to identity element and FOG is equal to the identity element in the domain of it is G, right? From this it is very clear that the first note is, if f is a function from this set capital A to this set capital B is said to be invertible function. Is invertible if, here not if, then this function is invertible, then this function f must be, it is both 1 1 and onto, right? So similarly, if f is any function from the non-empty set capital A to the non-empty set capital B is both 1 1 and onto, then the function f is always invertible. Invertible is always invertible. So another way we can also define this. Any function f from the non-empty set capital A to the non-empty set capital B is said to be invertible. Here, if the condition is that f must be is both 1 1 and onto, right? So suppose here f, it is a function from this set capital A to capital B is both 1 1 and onto. It is defined by y is equal to f of x. It is the 1 1 and onto function. It is defined like this, y is equal to f of x. Then it is both 1 1 and onto means it is the bisective function. So here every 1 1 and onto function, right? Every 1 1 and onto function is invertible. So this function is 1 1 and onto. It is defined like this. This function is invertible. How you define this inverse? Here the inverse of this function is the function. It is denoted by f inverse. It is from this set capital B to this set capital A. It is defined by. Here f of for each element, that is x is an element of A, that is x is equal to this as f inverse of y. For each element y in the domain of f inverse, its image, it means that under f inverse is f inverse of y is an element of its codomain. It is the definition. So here these are the definitions. This is the definition of the invertible function. So here, after this definition, now I am going to discuss the examples based on this definition. So example, now there is a 99 possibly 9 the examples on this invertible functions. Say example, consider. So the function f from this side capital R to capital R given bar, it is f of x is equal to 4x plus 3. 4x plus 3. Show that f is invertible. So and also find the inverse. Of f. So this is the 5-mark question in your examination. So there is a 99%. So that is the possibility. So 5-mark question on this section. Say here you can find its inverse by using the composition operation and also by using the 1 1 and onto function definition. So here by using the composition operation, how you can find the inverse of this given function? Here first write the given function. Here given function is that f it is a function from capital R to capital R. It is given by it is y is equal to or f of x is equal to f of x is usually denoted by y equal to this as 4x plus 3. This is the given. It means that each element x in the domain, the image of this element x under f, it is defined as 4x plus 3. Here the elements in the codomain are of this form, right? So here next we are going to find the how the elements are, the nature of elements are in the domain. Means y is an element of the codomain, x is an element of the domain. How the nature of x in the domain means that so the element in the domain how they are means that get the value of x. So from this given definition of the function, therefore y is equal to 4x plus 3 is the given function. It means that 4x plus 3 is the element in the codomain. So get the x is an element of the domain. After getting the value of x in the domain, next we define the one more function. It is the function from codomain to domain. Yes. So see, y is equal to 4x plus 3. Get the x value. For that, bring this 3 in this side. Plus 3 become minus 3. Y minus of 3 equal to 4x. This is the product. To get the x value, again bring this 4 in the side. Y minus 3 divided by 4 equal to x. X, it is the element of the domain. Here, the domain containing the elements are of this form. Domain the elements are y minus 3 divided by 4. In this way, the elements present in the domain. In the codomain, the elements how they are 4x plus 3. Right? So here, now we are going to define the one more function. That is here, we define a function g. It is from codomain to the domain. Codomain is R. That is R to the R. Here in this function, the domain become the codomain of the function f, and its codomain become domain of the function f. It is defined by. We define the function g. So by it is g of y is equal to, if you consider, so y is an arbitrary element in the domain of g. The image of y under g is how they are. Here it is this codomain is the domain of f. In the domain of f, the elements how they are. They are of the form y minus 3 divided by 4. Therefore, g of y is equal to y minus 3 divided by 4. After defining the function g, so f is the given function, g is the defined function. So after that, get the composition. Therefore, now it is g(f) of x is equal to, x is an arbitrary element in the domain of f. So get the composition from f to g. This is as g of it is f of x from the definition of the composition function. Say g keep as it is f of x. The value of f of x, it is given as f of x is equal to y equal to, this is 4x plus 3. 4x plus 3. Say it is g of 4x plus 3. Here g of y. Compare these two. Here 4x plus 3 is nothing but y. So g of y is defined as y minus 3 divided by 4. Say g of y means in place of y, we are going to replace 4x plus 3 in the definition of g of y. Therefore, g of y means y. It means that 4x plus 3. This is the y means 4x plus 3 minus 3. This minus 3 keep as it is. 4 divided by 4. This 4 keep as it is. This plus 3 and this minus 3, they are get cancelled. We get this as 4x divided by 4. Again they are cancelled. We get this as x. X is an identity element. It is the identity element in the domain of f, that is usually denoted by I. It is the identity function. So where it is in the domain of f, the domain of f is R, that is as I R. Next, again one more thing here. So get the composition. It is from f to z and get the composition from g to f, that as f o g of y. Y is an arbitrary element in the domain of G. This as f of G of it is as y. It is the definition. This is equal to f keep as it is G of y. The definition of G of y is y minus 3 divided by 4. Here f of G, f of y minus 3 divided by 4 means here f it is there in the form of f of x. Here if you compare this function with this function, here the value of x is y minus 3 divided by 4. This is the f of x means in place of the f of x value, that is 4x plus 3. Here in place of x, y minus 3 divided by 4 is there. In this definition, replace the value of x by y minus 3 divided by 4. That is as 4 into x value as y minus of 3 divided by 4 plus of 3. This 4 get cancelled. Therefore, here the remaining factor here y minus 3 plus of 3, minus 3 is cancelled with plus 3. We get this as y. This y is an identity element in the domain of G, that is usually denoted by I. So the domain of G is R. Again this as I R. Therefore, from this it is very clear that so here GOF is equal to, it is the identity element in the domain of F, and FOG is equal to, and FOG is equal to, it is also the identity element in the domain of G, right? The domain of G is R. So here from the definition of invertible function. So the definition of invertible function is that f it is a function from this set capital A to capital B. There exists another function g from capital B to capital A such that it is GOF is equal to the identity element in the domain of f. It is as RA, and FOG is equal to the identity element in the domain of G as IB. If so, the function f and g will satisfy these two conditions, then the function g is called as the inverse of f, that is usually denoted by g equal to f inverse. This g function is called as inverse of f, that is the thing. Here f is a function from R to R. Here in place of g, we are defining the function g. It is a function from R to R. It is defined like this. The composition of G and F. So the composition of G and F and G, we get the identity element in the domain of F. We get the identity element in the domain of G. It means that the function G is called as the inverse of the given function. So that is here GOF is equal to IR, FOG is equal to IR. It means that so G is called as inverse of the F, that is usually denoted by G is equal to F inverse. So this is the 5-mark example. So here first thing here is in this example, first write the given function, how it is defined. So the given function is like this, it is defined like this. Okay, so here he given the nature of elements in the codomain. The elements in the codomain are of this form, that are of the form 4x plus 3. Using this one, get the elements so in the domain, how they are. The elements in the domain are usually taken as x is an arbitrary element in the domain. What is the value of x? How the elements that are present in the domain. So get the value of x, that for the x value is y minus 3 divided by 4 So this is the arbitrary element in the domain. The domain containing the elements are of this form. Sorry. After that, here we define the reverse function. F is a function from R to R. Then we define the another function. It is the reverse. That is, its codomain to domain. Its codomain is R. Domain is R. It is defined like this. If you consider Y is an arbitrary element in the domain of G, the image of Y under G is G of Y. It is defined Y minus 3 divided by 4. Because so here the image in the codomain of G is the domain of F. In the domain of F, the elements present like this. E formula elements set. That's why G of Y is equal to Y minus 3 divided by 4. After defining the G function, get the composition. That is F to G and G to F. So if the composition is equal to the identity element in the domain of F and the identity element in the domain of G, then we say that this defined function is the inverse of this given function. This is the solution by using the composition operation. You can also solve this example by using the 1-1 and onto method. So as we are discussing, while discussing the definition, the invertible function, any function f from the non-integer capital A to capital B, it is said to be invertible. The condition is that this function must be both 1-1 and onto. Or any function f from A to B is both 1-1 and onto, then that function is always invertible. That is, inverse function is usually taken as f inverse is a function from B to A. It is B to A. Right? In this way, check first whether the given function is the bisective function or not. It means that it is both 1-1 or not. If the given function is both 1-1 and onto, then this function is bijective function. Every bijective function is invertible function. Write the inverse of the given function. For the 1-1 function, 2 mark. For the onto function, we get a 2 mark. So for the value of f inverse. So for writing the value of f inverse, again 1 mark. In this way, we get the 5 mark on this. So for this example, so first it is solution. It is 1-1 function. 1-1 means. So our definition says that any function f from A to B is said to be 1-1. The 1-1 correspondence means that the different elements in the domain have the different images, or if you consider the two arbitrary elements x1, x2 in the domain such that so f of x1 equal to f of x2. If you consider the images are equal under the given function, then 1-1 correspondence means the corresponding elements x1 must be equal to x2. This is also called as the 1-1 correspondence or the definition of 1-1. This is the thing. Or we may also define another thing, that is, if x1 or x2 are the different elements in the domain, their images f of x1 must be is not equal to f of x2. It means that different elements in the domain have the different images. These two are the 1-1 function definition. So here for the 1-1, I am going to define the two arbitrary elements. Let here x1 and x2 are the two arbitrary elements in the domain of f. It is as that. Consider their images. Consider that the image of x1 and x2 under the given function are equal. That means f of x1 equal to, it is f of x2. Consider here. So after considering the image of x1 equal to image of x2, then check whether the corresponding elements x1 and x2 are equal or not. If they are equal, then this function satisfies the 1-1 correspondence, then the function is 1. If they are not equal, then the given function is not 1-1. So here f of x1 means it is as by the definition f of x is 4x plus 3, f of x1 is 4x1 plus of 3. f of x2, f of x is 4x plus 3. It means that f of x2 means replace x by x2 in the our given function. It is 4 times x2 plus of 3. So to get the x1, x2, so first we are going to eliminate the constants because they are equal. This 3 is cancelled with this 3. After that, 4x1 equal to, it is 4x2. Again, this 4 is cancelled with this 4. We get this as x1 equal to x2. We get here, we are defining the arbitrary values x1 and x2 in the domain. So considering that the limits are equal, the corresponding elements are also equal, means this given function satisfies the 1-1 correspondence. So it means that the given function f is, it is 1-1. So for this 1-1 function, for this we get the 2. Next, check whether this function is onto or not. For the onto, so onto means each element, the definition of the onto function. Any function f from this capital A to capital B is onto here the each element of the codomain. Y is the image of some element. So x of the domain. It means that y is equal to f of x. Each element of the codomain y is the image of some element x of the, that is the elements of the codomain. If this condition is satisfied, then that function is called as onto. Or one more condition is that range of f must be equal to the codomain B. Then also you say that the given function is onto. So here, first we define the arbitrary element in the codomain of f. Codomain of f is also R. Let here y belongs to R is the arbitrary element in the codomain. Such that how it is? Such that it is the image, that is this must be image of some element x in the domain. So equal to 1. So here get that for each element y, the corresponding x value. So the corresponding x value, it is an element of the domain or not. For that, so here get the value of x with respect to the given value of y. For that, f of x value insert here. F of x value is 4x plus 3 equal to y. Therefore, to get the x value, 4x equal to this as y minus 3. Therefore, x is equal to y minus 3 divided by 4. Right. Y is an element of arbitrary element in the codomain. X is an element of the domain. Onto condition means each element of the codomain is the image of at least one element of the domain. It means for each value of the y, real value of y, resultant x value, it is y minus 3 divided by 4 is the element of the domain or not. Right? If for each value of y in the codomain, the resultant element is an element of the domain, then this function is always on. So here y is an arbitrary real number. So from the properties of real number, subtraction of two real number is a real number. Yes, y minus 3 is a real number. Divided by 4. 4 is a constant factor, constant real number. This is the real number. This is the constant non-zero real number. It means that division of two real number is again a real number. Here, for each real values of y in the codomain, the corresponding x value, it is y minus 3 divided by 4 is again a real number. It is an element of the domain. It means that this belongs to the element of, this is an element of the domain R. So it means that the given function, it is as onto function. So write that here for each y belongs to R. For each y belongs to R in the codomain, there exists an element x is equal to y minus 3 divided by 4 in the domain R. Domain is also same. Such that so the image of this element, that is as such that f of x is equal to f of x, image of this element under the given function f of x is equal to, it is, what is that? F of x means f of x value means y minus 3 divided by 4. It is y minus 3 divided by 4 equal to f of x. In place of x, replace this value. It is 4 into y minus 3 divided by 4 plus of 3. This 4 is cancelled with this 4. This as y minus 3 plus 3 plus 3 is cancelled with this plus 3. This as y. So here each element of the codomain is the image of some element x in the domain. Therefore, the given function f is onto function. F is onto function. Therefore, f is 1 1 and f is onto. It means that the given function f is bisective function. Every bisective function is invertible. F is invertible. F is invertible. So after that, how the invertible function is? So the inverse of this function is, it is usually denoted by f inverse. It is the function from f inverse. It is the function from the codomain of f to the domain of f. That is as R to R. F inverse is the function from R to R. Codomain is as, domain is as. It is defined by. It is defined by f inverse of y equal to. So the domain of f inverse is the codomain of f. The codomain of f inverse is domain of f. In the domain of f, the elements how they are? The elements are x is equal to y minus 3 divided by 4. Therefore, f inverse of y. So f inverse of y means, so f inverse of y. The f inverse of y present in this codomain of f inverse. Codomain of f inverse is domain of f1. The elements present in the domain of f are in the form of y minus 3 divided by 4. That are y minus 3 divided by 4. This is the f inverse function from R to R. It is defined like this. So for this 1 1 2 mark, for this onto 2 mark, and for the f inverse it is 1 mark. There, this is totally 5 mark example. So you can calculate the inverse of the given matrix by the composition method and also by the 1 1 on 2. So by verifying the given function, it is 1 1 and on 2. So remaining examples are discussed in the next class. Thank you.